if I were to choose a lab that we would do remotely, this would be it, because the procedure for this lab really isn't that involved. Okay, hopefully you watched the video and you saw, you just set the thing up and then you let it run and monitor the temperature and record the pressure every once in a while. That's it. All right. Nothing more fancy than that. All right. So essentially, as a holdover from the the pandemic is that we've we've done this, or we have all this data, and so each of you will be sent through Canvas an individual set of data. I've already sent out a few. Okay, I managed to get out 3 before we started because those people showed up early. All right, and um, that's. But the rest of you will get yours soon. All right. I'm making a note of things. Okay. All right. So what I'm going to do is present to you pretty much what I would have presented to you if we were in class. Really, the only difference is I'm not going to go over all the potential pitfalls for the setup because it's just not a good use of our time. All right. Then I will get everybody's data out to you. Okay. And where you're going to look is the Canvas mailbox. All right. And it's going to take me about 10 minutes or so once I stop to get the data out. And then, because each of you is going to get your own set of data. All right. Then I'm going to turn you loose. Now you have a choice. I'm going to stick around for a while. I'll stick around probably till about 1:30 on Zoom. And if you want to stick around and work things, that way, if you have questions, you can ask them. And people yesterday definitely took advantage of that. Um, and I recommend it. All right. And then once questions die down or 1:30 is reached, depending on which is first, I'll shut down. You can continue to ask me questions via email or text, whatever works. All right. Okay, so I'll try doing this a little bit differently than I did yesterday. Let's switch over to this screen. All right. So our objective today is to determine the heat of vaporization of water. And the way we're going to do this is we're going to make a Clausius-Clapeyron plot. All right. You're going to collect some data. Most of the data is going to be collected electronically. The purpose of this part of the lab report is I want you to understand how the calculations work. All right. And then what you're going to do is just take the rest of the data and put it into the spreadsheet. Now, the other thing is the spreadsheet is available on Canvas. It's the very first item under the lab module, clausius.xls. You can download it. You can open it either in Excel. Actually, you could probably open it in Google Sheets. The only problem with Google Sheets is you probably won't be able to draw a trend line. Okay, somebody told me that you can do that now, but it doesn't give you the same information on the graph that Excel does. All right, there is another way to do that. You could use slope and intercept functions and correlation function. All right, and those will give you the data. And if you want to figure out how to use those, I'm not going to tell you, but you can go and look online because I'm sure there's good documentation for Google Sheets. Anyway, so here's what we want to think about. Since we're going to be collecting more than 2 points of data, what we need to think about first of all is we're going to use the graphical version of the Clausius-Clapeyron equation. Something like that. All right. And basically, again, what this tells us, just like last week in the lab that I hope you turned in today, I can see that some of you have turned it in electronically. Anybody who doesn't want to turn it in electronically, you have a choice of a couple of things to do. You can give it to me next time you see me. you can give it to the lab coordinator, which I would recommend, and he'll give it to me when I come in. All right, I'm probably not going to come in at the earliest until Monday. So it's definitely in your best interest to scan it, because that way I'll get it done. I'll get done grading it this weekend. All right. And so what we can do is if we make a plot of natural log, oh man, sorry, I really screwed this up. It's not at delta H, it's natural log of vapor pressure. If we make a plot of natural log of vapor pressure versus 1 over temperature, then the slope of that line is equal to negative delta H of vaporization over R. Again, this should be familiar to you based on what you did last week, the part 3 of last week's lab. Okay, the difference is and this was a challenge when I first designed this lab. How do we measure this? How can we measure the vapor pressure of water at a series of different temperatures? In a perfect world, what we could do is we could evacuate a flask full of water so that only the water vapor inside the flask gives rise to the pressure in there, and seal that off. Unfortunately, the Erlenmeyer flasks that we use for this purpose or for this lab would not be suitable for that kind of thing because the glass is too thin. You pull a vacuum on those things, they run a risk of imploding under vacuum. I don't know if you've ever seen anything implode under vacuum, but it's not pretty. Okay, you get a lot of shrapnel, and it makes a loud noise. All right, so I don't particularly want to expose you to that. So instead, we have a quandary, because here's what happens. The total pressure that we measure, we're going to argue, has two components. You could carry it even further if you wanted to. If you wanted to break down air, but we're going to treat air as a single ideal gas. And what we're going to say is this: the total pressure inside the flask that we measure is equal to the partial pressure of the air plus whatever vapor pressure of water is present. Okay, now that poses a problem, because if we raise the temperature, both of these values are going to go up, right? The vapor pressure of water is going to go up if it follows the Clausius-Clapeyron equation, and the partial pressure of air is going to go up if it follows Boyle's law. Or I guess it's Charles' law. That's it. Anyway, temperature and pressure. Or it's actually the law of Gay-Lussac. That's right. So here's what we're going to do. We're going to start by cooling the heat of vapor, or our heat of vaporization apparatus, down, okay, to a temperature of 5 degrees or below. At that temperature, we're going to assume that water has no vapor pressure. All right, now, here's the first question. Is that a valid assumption? All right, can we make that assumption? Of course, the lower the temperature, the lower the vapor pressure. And some of you are going to have data with the temperature almost at zero. Some are going to have the data with a little bit higher temperature. It's real data. These are data sets that people actually collected in the past. All right. If that's true, then here's what we can say. At this temperature, okay, of less than or equal to 5 degrees Celsius, we can calculate what's called a Gay-Lussac constant. All right, I'm going to call it Kg. It's just K in the lab manual. And I can do that by dividing the pressure of the air by the temperature that it's measured at in kelvins. All right, so what you're going to do is at that low temperature, you're going to use the pressure inside the flask to calculate the Gay-Lussac constant. And again, if you go back to the data sheet for this lab, that's what you're doing over here as well. You're going to take that data, put it in here manually, and grind out the calculation, right? Then what you're going to do is you're going to use that Gay-Lussac constant to calculate the partial pressure of air at all other t's. Now you can do this by hand if you wish, but again, that's the point of the spreadsheet. If you take the data that you get, okay, and if you look at the data you get, it's basically two columns of data. It's pressure and temperature. Okay, I can't remember which is which. Pay attention to that, because what you can do is if you open that PDF in something like Google Chrome or Adobe Acrobat, you can just copy and paste each of those columns into the appropriate column of the spreadsheet once it's open. All right, it's easier than typing it in. Then look at the instructions in the lab manual about how you handle the spreadsheet. You've got to be really careful about, first of all, how you put the data into it, starting at the very top of the data column, and then also how you copy that function down. Because if you copy it down incorrectly, it's going to make a mess. All right, that's something you want to pay attention to. All right. So then what you can do is very simply this. You say, okay, I want to calculate the P of water at these other temperatures. I'm going to take the total pressure and you're going to subtract from that the partial pressure of air that you just calculated using the Gay-Lussac constant. Okay, now again, that's assuming that air has ideal gas behavior, which is a pretty reasonable assumption. All right. Again, the question you want to ask yourselves, because this is a question you're going to have to answer at the end on Canvas, is what are some of the flaws in this experiment? And there are some. All right, are you going to get a perfect delta H of vaporization for water? Probably not. All right. Again, what you should get if you've done this well, or I should say, if the person who collected your data did it well, because you really have no control over it, is if you make your Gay-Lussac plot, or excuse me, if you make your Clausius-Clapeyron plot, you should get points, first of all, that match a straight line, and second of all, have a negative slope. Okay, and again, you can think about that from last lab period, because you did exactly the same thing with another liquid. All right, that's pretty much it. If you can do all that, you're in good shape. All right, so let me talk about one other thing before I'm done with this. And of course, my computer's going bananas now. There we go. Okay. What are you going to turn in for the lab report? You're going to turn in this page, completed, and make sure you write down your calculations. It says to show your calculations below. Okay, make sure you do that. If you don't do it, you're going to lose some points. All right, now why do I ask you to show calculations? In part because I want you to tell me that you know what you're doing, but also I have an ulterior motive that is designed to help you, and that is when you go back in 5 weeks and review this for the first lab exam, you can see just what you did. So make your calculations nice and clear. All right. And then if you go to the next page, it's 2-page lab report. You have a calculation, and you're just going to write those things down. You're going to compare the heat of vaporization to a known value. Now, when you do this known value, you should reference it. Don't reference it. You're not giving credit where credit is due. It's a bad habit of general chemistry textbooks that they don't reference things. Don't follow it. All right. You pull it from the textbook. You give a full reference for the textbook and the page number. You pull it from the internet, which is legitimate. Just make sure you give the full URL. All right. Not just wikipedia.com. That's not good enough. Okay. That doesn't tell me where I have to go to find it. All right. The question, again, don't worry about answering the question. You do that online. All right, so this lab report is going to consist of these 2 pages and your Clausius-Clapeyron graph for your data. That's enough. Okay, if you want to include the spreadsheet as well, you're certainly welcome to, but you don't have to. It's the graph, the Clausius-Clapeyron graph that I'm interested in. All right, does anybody have any questions about that before I mute myself and finish sending out these the data?
Sorry, I think I missed something. Did you say I'm sorry, you said turn in the lab pages from Canvas and the Clausius-Clapeyron
That's right.
graph.
Yeah.
Was there a third thing? I think I missed
No.
something.
No.
Oh, okay.
Those are the things I want. I want the 2 pages from the lab manual and the graph. I said if you want to turn in the spreadsheet, you can. Okay, that's it.
Thank you.
Sure.